So this is the exercise, and actually the idea of it is to show how useful can be, for example, HSAF products, especially over data scarce regions. And so I want to thank again my colleagues for helping me to shape the exercise. And in this exercise, actually we pick a catchment in Africa, and we have a model, in this case HC model, of which the references are Brock et al. 2011 or Massari et al. 2018. And then we will have 5 different rainfall products. The one is GPCC, it's a gauge-based product. ERA5, the analysis product. We have EUMeTrain. We have H23, which is based on microwave observations and is released by HSAF. And also we have H64. And I prepare all the configurations and the file to run the hydrological model, so I won't go through it now because actually it needs lots of time. But I now go through the exercise. So the first thing to do is to import the libraries. We have created a library called milc_2, and this library contains the hydrological model and the different routines to calculate the score. Everything is written in Python, and I think it will be available to you if you want, and we can share it. And we will import pandas to manage time series, NumPy, matplotlib for plotting, and also basemap for plotting the catchment position. And also we will use calibration tool, algorithm, I would say, which is called particle swarm optimization. There is a specific routine that you can install on your computer if you use Python by using Pit, and the name of the library is PySwarms, and I will show you later how it works. So let's load it. And let's also plot the catchment position. You can see here is in South Africa, and the basin is not big. It's 400 kilometers squared, but this is relevant because so having hydrological simulation on a very small basin may be very challenging. So I'm happy that we have this small catchment because it's small in relation to the satellite footprint. Now let's take a look to the rainfall and discharge time series, and this is how the text, the file text that the model use for running the simulation. We have a precipitation, we have a temperature, and we have discharge. And this discharge, of course, is used as a benchmark. Then let's plot it. And this is the discharge. Even though the catchment is, quite not very small, because it's not 20 kilometers per catchment, it's 400. But the discharge is not really much, and you can see peak discharge up to 14 cubic meters per second. And these are the rainfall. Even the rainfall is not low actually for some of the events. This means that probably there is contribution of infiltration, or also the temperature there very high. Maybe the evapotranspiration plays a role. And then let me just say some few words about particle swarm optimization. This is I don't know how much familiar you are. It's basically an heuristic type of calibration. So it is not based on gradient, and it considers different particles. Each particle is a simulation basically, and it runs the calibration, and it assigns to the particle a social behavior, so they can move toward the optimal solution together by respecting some of the rules, and they move singularly by the behavior, like society. So it is try to simulate the movement of TW, you can say. And it converts actually, so it is not say that when we find an optimal solution is the real optimal one, but generally it works very well when the space of the parameter is very large and we have to find it. And then we calibrate 8 parameters which are reported here. For more information on this, you can go to the publication, to this link here. And the initial conditions, actually this would require a warm-up of the model, but in this case we just skip it and we calibrate these parameters. Then we have a field capacity, an exponent of drainage, we have a parameter for infiltration, and a one controlling the fraction of drainage and interflow. And then we have a coefficient for lag time relationship, so to tell how the catchment respond to the precipitation input in times, and so its ability to store water and release. And then we have a parameter for potential of transpiration and for runoff. Then we have to define our objective functions, which is based on basically on kg. So we have to say to somewhere that okay, we want to optimize the kg. So we have to, since kg varies from -infinity to 1, we have to just take the complementary to 1 to kg. When kg will be equal to 1, we will obtain an error equal to 0, which is our best solution. We will never obtain 0, of course, but this is our objective. And then we have to bound a little bit the parameter space. So we have to say to the particle swarm optimization where to look for the optimal solution. So we just consider these bounds. I won't go to them because, but you can just play with them if you want. And then we have to say to the particle swarm optimization how to organize the movement of the different particles. So how to control how to get close to the optimal solution. And then we have to optimize. We are ready to optimize. What we do here is to optimize, for example, with respect to GPCC. So we assume that GPCC, which is gauge-based product, is the best in terms of rainfall quality. And what we do here is to calibrate the model considering as a floating GPCC. And this is the calibration. It proceeds, and you can see we select the number of iteration equal to 20. And you can see that the model converts to the optimal solution. This is cost, is basically 1 minus kg. And this is what we obtain. Here on the top, we have the soil moisture distribution in one layer, soil moisture dynamics, sorry. In blue, we have the GPCC rainfall. And in green below, we have the observations, the benchmark, and in red, our simulations. And you can see that actually some of the peaks are not taken, and but generally the dynamic is followed, and we have some problem reproducing low flows, as you can see here, and some of the peaks. So it's not the best simulation, but actually kg is 0.7, so it's not bad. And the next uplift, which is much more related to peaks, this is not optimal, I would say. So probably I would prefer for a simulation like this to catch these peaks. But of course, we are talking about something GPCC very as a footprint of 100 kilometers per 100 kilometers on a catchment of 400 kilometers square. So I won't expect that much from it. But of course, this should be the best product in the area because it's gauge-based. And let's go ahead. And once we have parameters calibrated for this product, let's try to use ERA 5 rainfall with this parameter. And run the simulation, and then we obtain not really good results. So worse than before, even though the next uplift has increased a little bit, and we have some, I think in terms of peaks is a little bit better, but we have a lot of bias, and the rhythmic error also isn't optimal. Then we use the HSAF and with the same parameter of GPCC, and also the dynamic is taken as well, but the bias is large, and also the net uplift is not optimal. In this case, it's even worse than before. But we can also try with the other products. For example, H23. Okay, here the peaks seems too high, and there is a clear problem of bias here. Why? Because probably the rainfall of H23 is too much, and we will check it out. And we have the rhythmic error very high with a bias almost double than before. So it seems there is too much rainfall in the system, and what the model provides using GPCC calibrated parameters is too much discharge. But let's control what leads to the poor performance of H23 rainfall product. So what we do is to load the GPCC and load H23, and then we compare them and in terms of rainfall. And we calculate the correlation between H23 and GPCC and the multiplicative bias between H23 and GPCC. Multiplicative bias is basically the ratio of the mean of the two. And if we run, here is an information, is a plot showing the rainfall of GPCC in black and H23 in pink. And you can see that it is true, H23 has too much rainfall with respect to GPCC. And indeed, the multiplicative bias is 200%. The correlation is not bad. So it means that H23 contains information of the dynamics, but maybe overestimate a little bit the rainfall. So what we can do here to improve this, as I showed in the presentation before, one option is to correct the bias. So we can just multiply the H23 rainfall by a coefficient, which is the ratio of the mean of the two, to correct the bias. So if we multiply it, we will obtain a zero bias with GPCC in terms of mean, and then we will try to see what's going on. Okay, here we have corrected the bias and we reduce the rainfall, and now the two rainfall are much more similar. And then the bias, the multiplicative bias is 100%, which is correct because the ratio of the mean should be 1. And correlation, of course, is the same. And then we try to run the model with this new corrected H23 product. And you see the performance increased a lot. And the next uplift is the best among what we see before. And if you see here that the peaks are catched, and so the performance are pretty good. But also we can, in this case, we can try to recalibrate the H23 to see if a bias corrected product, and in this case is the simple product, not the bias corrected one. If the recalibrated, let's see if our performance increases. We have the simulation here, and yes, the performance has increased, and more or less we have similar effect. I didn't try to use both bias correction and recalibration, but the performance are mostly the same. So if we treat this product in this way, you see that it contains lots of information. Even if from the beginning it seems it doesn't have an intrinsic values, actually it does. And so with a simple bias correction, we can just correct the hydrological simulation. But this is true also for the other products, and let's try to do, let's recalibrate HSAF, for example. Well, Yeah, this is the performance, of course, improves, and we are larger than 0.6 OTG, and the net uplift in this case is not the best again, and this is probably due to the lower variability of the products. And let's also try with by merging to do a Cinterrain H22. So what we call H64. This product is H64, and if we run it, the calibration, okay, the performance are really good. It's more than 0.7, and so I like the simulations, and they are actually, they complement the others. So if we use H23 and S29 together, we obtain very good performance and very good, relatively good. And also we obtain a drastic reduction of the bias to 8 millimeters per day, and also volumes per hour. And let's see if we recalibrate also ERA5 values. Well, it improves, but improvement is not much, and the simulation actually remained more or less the same as before. Sorry, the scenario here, and also we can say that actually if we recalibrate ERA5, the results that we obtain are not the same, are not good as when we use H64. And so this say that actually the H64 is very useful in Africa, and even its performance better than the reanalysis, and in this case, for example, just for the mesh uplift, better than GPCC. So the lab is done, and if you have any question, I'm available.